Hi, Year 9 students. I'm Norman Wahlberger. And today we're going to talk about scientific notation some more. So we're going to ask, well, what is scientific notation? I'm going to introduce it. And another natural question is, what is it good for? Well, it's good for measurement and expressing numbers very efficiently, especially very large and very small numbers. And there's an interesting question of the relationship with significant figures or significant digits, also in a measurement kind of context. So let me start by explaining what is scientific notation. All right, so it's a way of expressing a number. Let's look at an example. The population of Sydney around 2014, which is roughly 4.5 million people. So 4,500,000. Now this is a very rough estimate, and it includes not just the official city of Sydney, but the larger metropolitan area, basically everybody who lives in the general area. Now this is the standard way of representing this number, and this is the scientific notation way. In England, this is sometimes called standard form, or standard index form. We'll just say this is scientific notation. So let's have a look at it. We're talking about 4.5 times 10 to the 6. So there's two parts to this scientific notation expression. On the left we have a decimal number, which we're going to call the digit part. And on the right we have a power of 10, which we're going to call the exponent part. And there's something special about this digit part. All right, so the rule is that the digit part has exactly one non-zero digit to the left of the decimal point. Here's the decimal point. To the left of the decimal point you see a 4. You see a single digit. That's a digit, that's a digit. So 4.5 is allowed. 3.8 is allowed. 1.7 is allowed. But 53.4 would not be allowed because 53 has two digits to the left of the decimal. 579.8 would not be allowed because that has three digits in front of the decimal. So in scientific notation we agree that to the left of the decimal there's exactly one non-zero digit. So 0 is not included. You're not allowed to say 0.5 times 10 to the 6. That is not scientific notation. All right, so it's a very kind of standard way of writing the number. It means that there's no scope for different possibilities. There's really only one way of representing this number in scientific notation. There are other ways of writing a number in the general form digit part times exponent part. For example, 4,500,000 could also be written as 45 times 10 to the 5th. That's the same. If we multiply 45 by 10 to the 5th, then the decimal point moves over 1, 2, 3, 4, 5. So we get that number there. Another way of writing it would be 0.45 times 10 to the 7. Then we would have to move the decimal place over 7 to go from here to here. Or, in fact, we could write 4,500,000 times 10 to the 0. Because remember, 10 to the 0 is 1. So there's lots of possible ways of writing this number as some decimal number times an exponent or power of 10. But there's only one way, which is scientific notation. We have to have exactly one digit to the left of the decimal. Here there are two digits to the left of the decimal because the decimal is really there. Here there are 0 digits to the left of the decimal. And here there are 1, 2, 3, 4, 5, 6, 7 digits to the left of the decimal. So these are all not scientific notation for this number. This one is scientific notation for this number. So having this standard form for scientific notation makes it easy to compare two or more large or very small numbers. And we'll see some examples of that later on. So one of the things that we want to do here with this discussion of scientific notation is get you more comfortable and familiar with working with very big numbers and also very small numbers. Now let's have a look at some other cities in the world and their populations. So I've told you that Sydney, where I live, has 4.5 million people, roughly. Now that's not exact because the last census was actually a few years ago. And even in a census, there's lots of possibilities for errors because people are coming and going all the time. You're not always going to be able to correctly register all the people that are in a city at a given time. And also there's a bit of ambiguity as to where the boundaries should actually be drawn, of course. So when we say that a population of a city is a certain number, we have to take it with a bit of salt. There's some potential for error there. We shouldn't pretend that we're getting something too exact. So even though Sydney is a pretty big city, there are lots of other cities in the world that are considerably bigger. Here are the top cities by population in the world currently. The biggest city in terms of population is Tokyo in Japan, which has about 35 million people. When we write 35 million in scientific notation, it's 3.5 times 10 to the 7. And why is it 10 to the 7? Well, to go from a decimal point here to a decimal point here, we have to multiply 1, 2, 3, 4, 5, 6, 7. We have to multiply 3.5 by 10 to the 7 to get 35 million. The second biggest city, and this was a surprise to me, I'll have to admit, is Guangzhou in southern China, which currently, the greater Guangzhou area, has 32 million people, which is 3.2 times 10 to the 7. I just automatically assumed that it was Shanghai because for a long time Shanghai was the biggest city in China. But Shanghai is in fact number 3 on our list with 29 million people, 2.9 times 10 to the 7. And then we have Jakarta, the capital of Indonesia, at 27 million or 2.7 times 10 to the 7. And then Seoul in Korea, 26 million people or 2.6 times 10 to the 7. And then Delhi, India, 25 million people, 2.5 times 10 to the 7. Karachi, Pakistan, 23 million people, 2.3 times 10 to the 7. And then Mumbai, or Bombay, 22,500,000 or 2.25 times 10 to the 7. Now in all of these, except for the last one, I've given you the total to what's called 2 significant digits. So for example, for Jakarta, I've said 27 million, and then there's lots of zeros here. Now these zeros don't mean that there are exactly 27 million people in Jakarta. That would be ridiculous. What it means is that there's roughly 27 million people and that I've rounded things up or down to the nearest million. So the actual figure might have been 27,314,507. But because we recognize there's a certain amount of error in that, we decide to put zeros in those places, indicating that we're not really entirely sure about their values. They're sort of placeholders here, but they're not really meant to be significant containing information. There's only 2 significant figures in this number, the 2 and the 7. And that's true for all of them, as you can see, except for the last one. In the last one, you're getting a little bit more information than you have in the other ones, because I've given you 3 significant figures. 22,500. I've done that actually because if I rounded this up to 23 million, then it wouldn't be clear what's the difference between Karachi and Mumbai. Okay. So I'm being a little bit more precise about Mumbai. I could go and be more precise about these other ones too, but I haven't. I'm giving you a little bit more information, and you can see that reflected over here in the scientific notation form, where we have 2.25 times 10 to the 7. So we're seeing 3 digits in the digit part, whereas in these other cases we all had 2 digits. So we can see there's a bit more accuracy, a bit more information the more digits you have in this digit part. And notice how the scientific notation very quickly allows us to compare these values. They're all having exponent 7. The power is all 10 to the 7. So we know that they're roughly about the same size. And the only thing that's distinguishing them is these various parts here, and it's relatively easy to see which ones are bigger and smaller. There's a very convenient way of expressing this information that also contains some information about the amount of precision that we're using to obtain the numbers. All right, I want to show you some other Australian cities and their populations. So we've already talked about Sydney having 4.5 million people. The next biggest city is, of course, Melbourne, which almost has as many people as Sydney, but not quite. And that's 4,246,000. So this is a little bit more of a refined estimate than the one I gave you for Sydney. We've done less rounding to get that number. We've still done some rounding, but not quite as much. And we can see that reflected in the scientific notation. It's 4.246. And let's just check it that it's 6 really is the right exponent there. Because if we multiply this number by 6, then the decimal place has to move over 6 to the right. So if it starts here, then we are moving 1, 2, 3, 4, 5, 6. So yes, indeed, if we take that number and we multiply by 10 to the 6, we do really get 4,246,000. So this is the correct scientific notation for this, because the digit part really has 1 non-zero digit to the left of the decimal. All right, the next biggest city in Australia is Brisbane, with 2.189 times 10 to the 6 people, 2,189,000. And then Perth, 1,898,000. And then Adelaide, 1,277,000. And then in terms of state capitals, Hobart, capital of Tasmania, is quite a lot smaller with 217,000. And that's reflected in the fact that the scientific notation for it has a 5 instead of a 6. So there's a visible difference between having 10 to the 6 and 10 to the 5. It's a power of 10 difference. And let's just check. If we multiply this number by 10 to the 5, then we have 2.17 multiplied by 10 to the 5 is 1, 2, 3, 4, 5. Yes, we get 217,000. Darwin, capital of the Northern Territories, 132,000, or 1.32 times 10 to the 5th. And Canberra, the capital of Australia, which has its own sort of separate territory, roughly 412,000, or 4.12 times 10 to the 5th. And one more city, which is not a very big city, it's more of a town, it's Gloucester, which is where my wife's from. My wife's family lives there, and I've spent quite a lot of time there. It's about 3 or 4 hours north of Sydney. Pleasant, dairy, farming, rolling countryside. And it has 2,300 people. And in scientific notation, that's 2.3 times 10 cubed, or 10 to the 3. So if we take 2.3, the decimal point here, and we multiply it by 10 cubed, we get 2,300. And so when we're talking about sizes of numbers, then really the first thing that we should look at is the power of 10 that's in the exponent part of the number in scientific notation. That's sort of the first business to look at in terms of trying to assess how big or how small the number is. Once you've gotten the range of the exponent, then you can look at the digit part to determine relative sizes. So you can see that scientific notation is a very efficient way of recording things like population, for example, just one of many possible uses. Of course, one thing you want to be able to do is to convert from the usual form of a number to scientific notation, and from scientific notation back to the usual Hindu-Arabic form for a number. So the simplest case is converting from scientific notation to the regular number form of a number. And what we do is we just multiply by the power of 10, moving the decimal point appropriately. In our last video, we learned all about multiplying and dividing by powers of 10. In other words, multiplying by positive powers of 10 or by negative powers of 10. Because remember, multiplying by a negative power of 10 is really the same as dividing by a positive power of 10. So since we know how to do that, converting from scientific notation to regular form of a number is very easy. So 4.5 times 10 to the 9. This is a different number now. Okay? This is actually the age of the Earth, roughly in years. This is 4.5 billion. 10 to the 9 is a billion. Now how would we convert this into a regular number like this? Well, we just take this 4.5 and we multiply by 10 to the 9. That means we have to move the decimal place over to the right 9 positions. So we have to use some more zeros that are to the right of this 5. Right now they're not doing anything. 4.50, 4.500. Those zeros aren't doing anything. They're not placeholders or anything. But they're convenient for us to think in terms of giving us somewhere where the decimal can go. So if we move it over 9, starting here, and then we move our 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice that we've ended up adding 8 zeros, not 9, because the decimal point has actually moved 9 places. So 8 of them corresponding to those zeros, and 1 of them corresponding to moving past the 5. So 4.5 times 10 to the 9 is in fact 4,500,000,000. And that's the rough estimate to how long scientists think that planet Earth has been around. Currently, people think that the entire universe that we currently know is maybe around 13 or 14 billion years old. Just an idea. It may or may not, in fact, be true, but a lot of people think it's something like that. In which case, the age of the Earth is roughly 1/3 of the entire age of the universe. So it's actually been around for quite a long time. Here's another example of converting from scientific notation to a regular number, where we have a negative exponent. Okay, so 4.267 times 10 to the minus 2. That's scientific notation because we have a power of 10 and we have a decimal part that begins with 1 digit to the left of the decimal. So how do we evaluate that? Well, multiplying by 10 to the minus 2 is just the same as dividing by 10 to the 2. In other words, it's like dividing by 100. All right, so when we're dividing by 100, we have to move the decimal place over, but we have to move it over to the left, make the number smaller. So over here, it started over here, and we're moving it over 2 to the left. 1, 2. So we have to introduce another 0 to give the decimal some place to move to. If we put a 0 over here, it would be kind of meaningless, to say, well, it's 4 ones and 0 tens. The 0 tens doesn't mean anything. But here, the 0 definitely means something. It's now the placeholder in the 1/10 column. By the way, this number, which we introduced in our last video, is actually the width of a golf ball in meters. So when you play golf, golf balls all have pretty well the same size. And that's important because if you had different balls of different sizes, they would have different aerodynamic properties and the game wouldn't be fair. So it's important that everyone knows that the width of a golf ball is rather precisely specified. And for those of you who might be watching in America, let me remind you what a meter is. All right, here's a meter. This is our standard metrical unit from here to here. It's just a little bit bigger than a yard. Okay, so a yard is just 3 inches less of a meter, roughly. Okay. So when we're saying it's 0.04267 meters, it's really 4 and a little bit 4/100ths of a meter. How much is that? Well, that would be 4 centimeters. So it'll be roughly like that. Okay, another example. 5 times 10 to the minus 3. Converting that. Well, in this case, there's no decimal point that's visible. But of course, you know that if there's no decimal point shown, it's actually just to the right of the ones place. So multiplying by 10 to the minus 3 means we have to move that decimal point over to the left 3 places. 1, 2, 3. Or over here, 1, 2, 3. So when you're writing it down, you have to write down the 5, and then you have to write down a few zeros so that there's enough to move the decimal point over 3. And this is roughly the length of a red ant in meters. Okay, it's not that much different from this, but it's 10 to the minus 3, and this is 10 to the minus 2. So 10 to the minus 3 is 1/10 of 10 to the minus 2. Of course, there's a bit of difference between 4 and 5, but roughly it's about 1/10 of a golf ball, or maybe about an 1/8 or something like that. All right, so that's how we go from scientific notation for a number to the usual decimal form of a number. It really just involves multiplying and dividing by powers of 10, which we learned in our last video. The other thing that you, of course, need to be able to do is to go from an ordinary decimal representation of a number to scientific notation. So that's sort of reversing the procedure that we just explained. There's sort of 2 steps to this, and what I want you to do first is to write down the digit part. Okay, and that's exactly the same as the number that you've got, except that you're going to write it in such a way that there's only 1 digit to the left of the decimal. And I should also say that in general we ignore zeros at the end. And then after that we determine the required power of 10 that we require in order to ensure equality, to make sure that we've actually got the right power of 10 so that the 2 things are equal. Let me illustrate it here with 412,000. To write that in scientific notation, I would take the decimal part, 412, and I would write it as 4.12. It has to be in that form because we have to have exactly 1 digit to the left of the decimal. And then I have to multiply this by some power of 10. Well, what power of 10 do I need to multiply this by to get this? Well, that's asking, where does the decimal point have to go? It's starting here and it has to end up here. It has to move to the right 1, 2, 3, 4, 5 places. So we have to take this number and multiply by 10 to the 5 in order for this to equal this. How about this number here, 0.0001? Well, the digits are just 1. Like maybe I could write 1.0, but I don't have to, but let's say I could. Okay. All right, so we've written 1.0, and now we have to multiply by an appropriate power of 10. What do we have to multiply this number by in order to get this number? Well, the decimal point has to move from here to here. So over here, it's essentially starting here, and we have to move it over here. 1, 2, 3, 4 to the left. That's making this number smaller, so we have to multiply by 10 to the minus 4. In other words, that's really dividing by 10 to the 4. Okay? Dividing by 10 to the 4 shifts the decimal place over to the left. Multiplying by 10 to the 4 shifts it to the right, so dividing by 10 to the 4 shifts it to the left. And dividing by 10 to the 4 is the same as multiplying by 10 to the minus 4. So there is the scientific notation for this number here. Oh, by the way, what is this thing? This is the width of a human hair in meters, roughly. And what about this very big number? If we put commas, ones, tens, hundreds, thousands, millions, billions. This is 9,460,528,400,000. How do we write that using scientific notation? We start with the digit part and write 9.4605284. And I could keep writing zeros, but I'm not going to, because zeros at the end of a decimal like this really have no effect on the size of the number. And now I have to multiply by a certain power of 10. And I have to ask, what do I have to multiply this number by in order to get this number? Well, it's probably best to go back up here and say, okay, suppose I start with the decimal point there, which is the one I've got here. What do I have to multiply this by in order to get the decimal point over here? I have to multiply by 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. So this number times 10 to the 12th is this number. Remember, when we write equality, it means that this actually has to be equal to that. They have to be the same. And what is this? This is how many kilometers in a light year. Right? How many kilometers in a light year? A kilometer is 1,000 meters, which is about 0.6 of a mile. Well, it's a very large distance. Still, compared to the size of the universe, this is still ultimately not such a big unit when we are talking about galaxies and the distances between galaxies and so on. But it illustrates the kind of big numbers that we need to work with in science and that are dealt with very efficiently with this scientific notation. All right, so in our last topic today, we're going to talk about comparing numbers using scientific notation. Scientific notation makes it pretty easy to compare the sizes of numbers. So here are three numbers: 3.892 times 10 to the 4th, 8.07 times 10 to the 5th, 2.1153 times 10 to the 6th. If we don't look too closely at this and just have a look at this 4, already that's telling us quite a lot about roughly how big this number is. So this might be rather complicated here, but we can ignore it to a certain extent and still get a sense for how big this number is. Why? Because we know this number is at least 1. Right? Because we've agreed that there's at least one non-zero digit to the left of the decimal. So this number is at least 1. And moreover, this number is at most 9.999. It's at most 10. 10 is the absolute maximum that it could be. So the smallest possibility is that we get 1 times 10 to the 4, which is 10 to the 4. And the biggest possibility is 10 times 10 to the 4th, or 10 to the 5th. So what we're saying is that any number of the form something times 10 to the 4, if it's in scientific notation, is between 10 to the 4 and 10 to the 5. This number, we just look at it, we see that there's a 5 there. That means that it's somewhere between 10 to the 5th and 10 to the 6th. This number has got a 10 to the 6th there. We know that this whole number is somewhere between 10 to the 6th and 10 to the 7. In particular, it's obvious that this number, this first one, has to be less than this number, because this 10 to the 5th is bigger than this, and this one is bigger than 10 to the 5th. So this has to be less than this one. And similarly, this has to be less than this one. So we can conclude immediately of this inequality between these three numbers. This is the smallest, this is the second smallest, this is the biggest, and we can figure that out just by looking at these exponents. We don't need to worry about what these digit parts are. So the basic rule is that the bigger the power of 10, the bigger the number. Very simple. And then the second rule is that if the powers are equal, well, all right, then you have to look at the digit parts to see which one is bigger. So, for example, suppose we're working with some negative powers, and these rules apply equally whether we're talking about positive powers of 10 or negative powers of 10. 4.2 times 10 to the minus 3. 4.7 times 10 to the minus 3. 1.3 times 10 to the minus 2. 9 times 10 to the minus 2. Just by looking at the exponents, what we can deduce immediately is that this number has to be less than this number. Going from minus 3 to minus 2, we're increasing, getting bigger. And so this number is bigger than this number. However, if we look at these two numbers, just looking at the exponents doesn't tell us which one's bigger because they're the same. So once they're the same, then we can say, all right, what about the digit parts? This digit part is 4.2, that one's 4.7. 4.7 is bigger than 4.2. All right, so this number is bigger than this one. And if we compare these two numbers, the exponents are both minus 2. So we can't tell at the level of exponents. So we have to look at the digit parts. 1.3 compared to 9. Obviously 9 is bigger, so this is the bigger number. All right, so comparing numbers, pretty easy with scientific notation. First thing you do is you look at the exponent, the power of 10 involved. And then if those happen to be equal, then you look at the digit parts to determine which of the two numbers is bigger. All right, great. So time for some practice. Okay, so our practice problems, pretty straightforward, I think, today. I think you'll find this relatively simple. Okay, to first of all write out as decimal numbers. So here we have some numbers in scientific notation. I want you to write them out or convert them into ordinary number form as decimals. And the second question, to go the other way around, to take numbers which are pretty well in standard form, or maybe pretty close to being in standard form, and to rewrite them in terms of scientific notation. And then finally, to take these numbers, and there's 1, 2, 3, 4, 5, 6, 7, 8 of them. Some of them are in scientific notation, some of them are in standard form. And to write them in increasing order. Increasing order means write the smallest one first, and then the next bigger one, then the next bigger one, with the biggest one at the end. So increasing order. All right, good. So we're getting a good feel for scientific notation. Next time we're going to carry on and talk about significant figures a little bit more. Connect a little bit more with how scientific notation arises in measuring things out in the real world in science. Scientific notation allows us to be rather precise about the amount of accuracy involved in a measurement. It's another really good thing about it. And once we have that under our belt, we'll also do a little bit of arithmetic with numbers in scientific notation form. So I hope you'll join me for that. I'm Norman Wahlberger. See you all next time.